Welcome everyone for the Shields Up Webinar 3. Today we are going to talk about how to protect your IP in a cloud-connected world. I have the great privilege of, we have a guest speaker today, and I have the privilege of inviting Dr. Richard Hayden, who is the CTO of Trustonic. He's got over 20+ years of experience in not only developing software, but also from a security and building secure subsystems for multiple market segments, automotive, banking, and all the other things. And he's going to share with us his philosophy on security and an approach on how we could protect our IP in cloud-connected applications. So with that, I wanted to pass on the speaker baton to Dr. Richard. Richard, it's all yours now.
Thank you, Anand. Hello, everyone. So let's get started. So we're talking today about protecting IP, but let's talk a little bit about what we mean by IP. There's different types of intellectual property in different devices and different reasons that an attacker might be interested in them. At one level, you can think of it in terms of code. Software, as much as hardware, has high value today, whether these are algorithms for doing an AI algorithm or for detecting if somebody is swimming or running or jogging, or any other sort of codec. Codecs can be extremely valuable, and attackers will want to steal them, and that might be by buying a device and abusing it. It may be in the supply chain. It may be somebody you can't trust in the supply chain who wants to steal your code. As well as your code, when we talk about IoT devices, we assume that the device at some level is talking to a service. So you need to know that the devices that are connecting to your service are themselves legitimate. If you make IoT devices and your business model is based on selling those devices, then you really don't want somebody building their own devices, fakes of your devices, and calling your services and abusing those services. You need to know that the devices that can use your service are legitimate ones that you've manufactured and sold. That brings us on to data itself. If I have IoT sensors which are generating data, then I may need to rely on that data for important business decisions, whether that's medical data or whether it's leading to changes in government policy or turning on and off streetlights. Whatever I'm doing, the data is only valuable if I can trust it. So if an attacker can break and steal and fake data, they may steal your data and use it for their own purposes, or they may fake it. And there's been many attacks where simply adding fake data into a data stream can abuse a device and break it significantly. And fundamentally, by all of these different means, an attacker can steal your business from you. They may fake the physical devices you make. They may do something in the supply chain, so you build the devices, but you don't profit from them. Or they may just break you in some other way by meaning that you are no longer trustworthy and you lose your customers in other ways. There's lots of different ways in which your intellectual property can be attacked. It isn't simply about something like, say, encryption. So this is a little analogy. Security is hard. It's like climbing a mountain. There's a number of things you can do, and none of them are really very easy to do if you just set out to go it alone. The most important part of security is often about isolation. It's about making sure that the code that you write, the attack surface is as small as possible so that your software is likely to be safe. Many attacks that have happened because there was a fault in a seemingly unimportant part of the system. Somebody found that there was a bug in the TCP stack, or there was a hardware side channel, or whatever, and found a way in to your code. So isolating the critical parts of your code is really the first line of defense for security. We hear a lot about encryption and signing and other cryptographic techniques. These are important for security, but they're not the be-all and end-all. We usually talk about them protecting data on the wire, or at least off the device, as may be in transit in the internet. And this is very important. If you have a system where the device is secure, but the data, once it leaves that device, can easily be intercepted or faked, then there's many ways in for an attacker. And then there's numerous types of hardware security. And there's ways of protecting code and keys against theft and against attack. And we all know about things like bank cards, which are very difficult to break because they have hardware security. But hardware security can be used in a number of different ways in different places. And one of the major things that it can protect against is device cloning, where somebody copies your software or steals your software and creates additional devices which they're making money off and you're not. So the first point I would always make on security is good enough security is a really, really bad thing to think of. You can't afford to make very many mistakes. The attacker has only got to get in once. And once they find a way in, they can undermine your business completely. So you need a secure foundation. You need a way of doing security which will mean that you won't make any mistakes, because it doesn't take very many for an attacker to get their way in. The other part about security, and we found this time and time again, is when you come to building, you think you have this mountain to climb, and then you find that actually that's only half of the problem. It's more of an iceberg than a mountain. You've got the security features you know about, the encryption or the isolation or whatever it is you want to do. But under the surface, there are many things you have to get right, and if you don't get them right, you won't have a secure device. So secure provisioning, how you flash the secure software and keys, how you update that software, how you attest or prove that that device is genuine or the key is genuine. These are very important things. Without those, you can't really build the security features. And then the low-level secure foundation, secure boot, but also power management, interrupt handling, secure debug, handling things like data flash so that you have a secure way of handling data within flash, controlling the MPU correctly, dealing with things like tamper detection. There's an increasing number of features that come on chips, but if you don't use those features correctly, you won't have a secure system. So the first message and the main message to take away from this is DIY security is a really bad idea. Security is a specialty. There's a lot to get right. And even simple features like encryption. AES is a standard encryption. You get an AES API, you go use it. That may seem simple, but the number of pitfalls is immense. You talk to the crypto experts and you find out if you don't use the initialization vectors correctly, an attacker can easily reverse your keys. So basically, don't do security yourself. You need a platform approach to security. You need somebody who is an expert to guide you up the mountain to make sure you do it properly. With the right tools, though, security is not that hard. Trustonic, working in partnership with Microchip, we've focused on building a secure platform so you can focus on building your application. And where you need to encrypt a message or prove a device is genuine or do something else, we can give you the tools to do that in a way that is safe and means that you can be certain that you're building a solution which is secure, but without having to be a security expert. So a little bit about Trustonic. Trustonic as a company is a joint venture that was formed by ARM, the chip makers, and Gemalto, French security company. And we've been around 5 or 6 years. And we were formed to exploit TrustZone when TrustZone first came out in application processors, A-class CPUs. And we have about 2 billion devices running our secure operating system and our security foundation today. And these range from phones to cars to larger IoT devices. What we've done more recently, and what we've done in partnership with Microchip, is we've turned to the M-class devices, and with ARM producing TrustZone M, or M-class TrustZone on the M23 devices, we've worked with Microchip to build a solution which takes those secure capabilities offered by ARM in their chip level, plus Microchip's security features, and we added the software layer to provide a secure platform, which just like every smartphone or smartwatch or smart car, gives you a foundation to build security on top of. So the particular device we've been working on, the first one we've done in our partnership, is the SAML11 KPH. Now KPH stands for Key Provisioning Host, and it's a code name for some of the technology that we use to add the security to these devices. And the way this works really is in 3 pieces. First of all, you get a regular SAML11, which has TrustZone on it. That provides hardware security features. So TrustZone itself divides the chip into 2 and gives you a secure and a non-secure world, as we call them, to write your code. The idea being by putting some code into the secure world, it's isolated from the rest of your code and therefore makes it harder for an attacker to get to it. There's also low-level technology for doing things like secure boot. There's MPU isolation possibilities, and there's a lot of security features which, if properly used, can build a great solution. What Trustonic does on top of that is really two things. We add what is really just a micro operating system. We call this a micro trusted execution environment. And it's a small security layer that runs in the trusted world together with secure boot and secure update and other capabilities. And it allows multiple security modules to be run which are isolated from each other. And we provide simple APIs to let you secure code that runs inside these modules to do whatever it needs to do. We also provide a bunch of modules in the box, as it were, to help you do the sort of things that people commonly need to do, such as encrypt messages. We also, and this is where the KPH terminology comes in, we add a unique device key to every device. So every device comes pre-provisioned with a key straight at the chip level, and that's something that you can build on top of, and you can use that to prove the device is genuine or to establish secure communications and so on. It gives a lot of power, and I'll talk a little bit about that in a moment. And finally, the last stage is up to you. You add the application code, and some of that will just be running in the normal world for doing normal work, non-security things, focusing on the application. But where necessary, you can add your own security modules to perhaps control the peripheral, or to manage a key, or to do something else which is security sensitive. They can use the high-level APIs that we provide to do security capabilities, or you can access hardware directly. You can say this particular pin, this particular interrupt, this belongs to this particular security module, and only it can talk to it. And that allows you to write very low-level software if necessary, but giving the isolation that you need for good security. So to get started, what you need is to just get a bog standard SAML11 Explain Pro development board. This has a SAML11 on it, and with the SDK that's freely available for download, and the link's on the page, you can download a toolkit which lets you experiment with our SDK and build your secure devices. In production, you need to use the SAML11 KPH, which is the SKU of the SAML11, which comes with our system pre-installed and that pre-installed key. And there is a production SDK to help with secure flashing in the factory for production use. In terms of how to build your system, the security is based on the concept of trusted modules. So each one of these modules is just a chunk of C. It's just a little bit of code. They have a single entry point, which is how they're called, to say, please do something security related. And that can be called either by another module or an interrupt or other event. And each module can own its own private resources. So it can have some data which belongs just to it. It can have some code. It can have some persistent flash, interrupts, whatever else it needs. And you can do whatever you like within that module. So you can access the hardware directly, or you can write some relatively high-level code. The modules themselves, though, each one, because it can securely identify who calls it, it means it's very hard to attack. It will only do what it's asked to do, and it will only do what it's asked to do by the right person calling it. And it, in turn, can call other modules. So typically, these modules are very small, and they can reuse components which are built to do things like encryption, to write to flash. So we have a transactional data flash module which will let you store keys and values in the data flash on these devices, and we'll do all of the difficult problems of making sure we do transactional update and only allow the module who owns a particular key to write to that flash. We also provide modules for things like secure power management, for controlling the UART, and so on. So there's a whole bunch of tools, but the important point here is that you can write your own to do whatever you need to do. So if our secure power management is not good enough for you, you can write your own, and it will get all of the protection, the same level of protection that ours does. So I'm going to give you an example, and I'm going to show some code here, but really the point is just to show you the structure, not a line-by-line code. So a common thing you might want to do is say, well, I need to sign some messages or encrypt some messages to send to a web server, but I want to make sure that nobody else can ever see that key. So I'm going to create a little module which is going to encrypt messages, encrypt data with a key, and then output that data. It has a very standard little API, which is what we call the entry point, where we pass in a command, and this command in this case is going to be called Encrypt. It's just an identifier, and we're going to pass in some buffers. And what it's going to do is it's going to check that we've passed in the right shape buffers. This is a sort of standard pattern, and we use Global Platform Standard as a calling convention so that this is familiar to people who've done this sort of thing before. We're then going to call another module, and this is the secure storage module, to say, hey, can you retrieve that key that I stored earlier, so that we use the same key every time. And the storage module, because it knows who calls it, will only reveal that key to this particular module. So nobody else can ever read that key. So that key can be read in. And in the SDK, we actually give examples, which are a couple more lines, but only a couple more lines, which show how to read that into data flash and use all of the hardware capabilities of this device. Once I've got that key, I can then call another module to say, hey, now I've got a key and I've got some data. Please can you do the encryption? And then pass the result back out again. So it's very straightforward coding. And the important thing here is that this module is the only thing that ever gets to see that key. And it's building on those building blocks that are built, that we've already built for doing things like secure storage and for cryptography. So it's a very easy thing to write, but it's very highly secure. There's no way anyone can get at that key other than by calling into this module and executing the command encrypt, or one would assume you might have a command decrypt or command generate new key as well. So the point here really is that it's very modular and very straightforward to build secure code. We worry about the isolation. We worry about the complex things like cryptography and transactional flash, and you focus on the application itself. Now that brings us on to the idea of having a unique key in every device. As a security guy, this is a very powerful feature for me. What it means is that every device has the ability to show to a web service that it's genuine, and we have some services and examples as to how to do that. It also, because it has its own key, we can bootstrap things like secure communication. So if we want to talk to a cloud, we already have a key that we can arrange that the cloud knows about, so we can have secure communication. And now we've got that channel, we can do things like just-in-time key provisioning. So whereas traditionally for devices, you have to bake all of the keys that device needs in factory, you have to go to a programmer and pay for them to put the right keys into the device. This gives you the option of doing that at runtime, of waiting until the device first comes online and then pushing keys dynamically. And we have some examples in the SDK which show how to do this. We can also use that to protect against things like cloning. Because if I copy your design or copy your software, I can't copy the key. And because I can't copy the key, my clone is no longer perfect. It now has a missing gene, as it were. And that means when the clone tries to connect to the cloud, we can spot the difference and we can deny service. So this can protect against supply chain and other frauds, but is also a building block in which you can do a lot of things which security guys get really excited about, like creating secure channels. Just to touch briefly on code IP, our production SDK that we provide for secure flashing allows you to add modules into a device which is already protected, so that when those modules are added, they're sort of write-only. We keep the key, we keep other modules that are already present in the device, and we can add new modules. That means that if you then pass that device on to somebody further down the production line or to another factory, they can use those modules, but they can't read them back out again. So this is protecting at the code level, it's protecting your IP against reverse engineering. It prevents people from using a debugger port to read that back out again. And this is very powerful in enabling people to build parts which need to be customized further down the production line. But it's just another example of a different type of IP you want to protect and that we can protect using this. So to tie this all together, let me just sort of walk through a high-level example. So imagine we have a little IoT device. This is a heart monitor. And the job of this heart monitor is to take readings of the patient's heart rate, a little ECG, and to send those up to a cloud service so that a doctor can monitor it. Now, this is a medical example, but you could imagine the same sort of thing from an industrial IoT world, or even in a car, trying to take engine readings and use those for diagnostic purposes. So if we look inside that device, it might consist of a SAML11 as its brain, together with a few other modules, maybe one for display for some pretty lights for the end user so they know it's all working, and a communications module, which maybe is using Wi-Fi or Bluetooth to communicate externally. There's also going to be some sensors which are actually taking the heart readings for the patient. And that's what we want to secure. We want to make sure that those heart readings can get to the cloud without anything getting in the way, anything breaking. So in terms of code, we've got some general purpose application code. It's going to do some UI, it's going to do some communications, it can deal with the buttons and the bleeping and everything else. That's all running in what we call the normal world. It is not as security sensitive, and we don't really get in the way of that code. In the trusted world, though, we have a number of modules. We have a secure sensor, which owns the particular pins and interrupts related to those sensors. We have a little secure application, which is responsible for getting a reading and encrypting it and preparing it to be signed off. And it owns some keys and data. We've got some modules that we've got built in, which use the hardware crypto to provide things like AES encryption, and the attestation, which has the ID of this device. And the way we wire this together is we get our general code to just call out in turn to each of those modules to take a reading, ask for it to be encrypted, ask for it to be attested to prove that it came from this device to create an encrypted bundle, which can then be sent out to the cloud. So the bits of code are pretty standard, but because we've isolated them, it's very hard for an attacker to get in. They can't get at the key that's used for signing. They can't get into the sensor and break those sensors. And things like the crypto and the attestation are just modules that you can reuse. So the isolation that we put in place here minimizes the security cost because we haven't really had to do anything to get that isolation other than use our solution. It doesn't affect the main code at all. These are just functions which get called at the right time, so you don't have to change the way you do things. And the modules themselves can be reused. So the crypto module and the attestation module are ones that we provide, but your sensor logic could be reused in a different device for a different purpose. Because it's just a set of C functions that you can reuse, and it owns the hardware it needs to own. It's very hard to attack this, but it's also very hard to exploit bugs. If it turned out that there was a bug in my display module, or I'd done a bad job of my HTTP processing, it doesn't matter because it's isolated from the security. So that makes it easier to certify that this is a good solution if you need to certify it, and makes life hard for the attacker, which is the job of any security software. And then the attestation adds an extra layer of value. It means that when this thing talks to a service, we know not only that the readings came from a particular device, but we can say this definitely came from one of my Model X devices. It couldn't have come from a cheap knockoff of my device. It couldn't have come from somebody else's device. And then that allows you to enable things like end-to-end encryption and privacy. By doing this, we're doing end-to-end encryption, and privacy really is something that you get as an important application for much of this data, and encryption is sort of the mechanism for doing that. So to sum up, hardware security with secure provisioning can prevent theft of code. That's one type of IP we want to protect against. The IP security people always talk about is keys. And the key management and the device key, the unique device key we put into every device, allows services to identify legitimate devices and makes it much harder for rogue devices to abuse those services because they don't have the key, they don't know, as it were, the password to identify themselves, so the services can easily ignore them. And this is probably the most important piece for anyone building a large system relying on small sensors. As a result of this, you can trust the data which is generated by your system because the foundations are secure. And that in turn means that your business is protected, whether your business is in building the device or in aggregating the data and using it. Whatever it is that you business do, you can focus on that and on writing the application logic, and we can focus on the security. So thank you very much. That was a quick run through the value that you can get by using a secure platform on a small device.